All right, welcome to lesson 2.4. So this is Do You Have 5 Seconds? This is lesson 2.4 notes. 2.4 notes is going to be our first introduction to something called the normal distribution or the standard normal curve. It's got a couple different names. Um, it's a pretty simple concept to do, but it's not a simple concept to understand. Um, to understand the way that this works. And so before we get started, I'm going to give you the same kind of introduction that I gave the AP Stats kids. And I want you to visualize this. We learned last unit or last notes that this is called a density curve. In this case, it is symmetrical and unimodal. Um, but it has a special name known as normal because it is symmetrical and unimodal. The mean, the median, and the mode are all the same value. So the mean, the median, and the mode are all in the middle here at 0 standard deviations. So in this case, they're telling us that that mean is 5.2, 5.02. Um, but in reality, it could be any mean at all. So this curve is constructed by taking the mean and putting it in the middle, and then you take the standard deviation and you count up and down depending on which direction you're going. So if you're going to the right, the numbers on the number line get bigger as you travel to the right. So instead of 5.02, this is 5.12, right? You're counting up by this amount for every one standard deviation you increase. Same thing here. This is 5.22. And this is 5.32. You're counting up by zero point 0.1 each time because that's what the standard deviation is. Same thing going the other way. If you're counting down, this is 4.92. Counting down again, this is 4.82. Counting down again, this is 4.72. And this is important because it kind of um, splits up our data, and this is where it gets weird. So just go with it. I want you to visualize this density curve. We know it as the density curve. It's called the normal curve. I want you to visualize this. Let's shrink the dot size. I want you to visualize this as a giant anthill. So as you can see, I am just making specks of sand on this anthill. It should be very clear that if I were to sit here on the recording or stand in front of you guys in the classroom and attempt to do this, that this would take me a very long time to fill out this entire curve with grains of sand. So I'm going to stop here and hope that you kind of get the metaphor, but I want you to visualize each and every one of these little specks, these grains of sand, as a data point in some infinitely large sample. All right, so these data points here, it's technically about the stopwatch thing that we would have done in class, stopping exactly on 5 seconds. But this could be about anything. This could be the mean IQ of 100, and then you count up and down by 15 because that's the standard deviation for IQ. So instead, this would be 100, and then if you count up by 15, this would be 115. You count up again, that's 130. So what we find is, and obviously these questions here, the 2 through 5, these are really easy to answer. What value is one standard deviation below the mean? Well, it's just any of the numbers we filled in. So this is 4.92. One standard deviation is one standard deviation above. This is 5.12. So the percentage of the values in between these. Now, these would kind of be like your guesses, but I'm going to go ahead and give you the official, like the real answer right away, is that there are percentages that you simply memorize because they're always true. So in fact, this slice right here up until the mean, so this piece, this is 34% of the data, and it just happens. Just source, just trust me, bro. So over here, it's the same thing because it's a symmetrical curve. So this is 34% of the data here, right? Up until this line. And then this chunk is 13.5 or 12.5? I don't remember. And it's not on the answer key. That's strange. Empirical rule. I totally spelled that wrong, but that's okay. So here is the standard normal curve. So you keep kind of labeling each slice, and they take on these values here. And you can see this in just about anything. If you like ran some kind of simulation, it would just approach this. And let's break this down and think about it for just a moment. This, in this case, is about the weights of cats, but it really doesn't matter what it's about. So that's a YouTube video. I don't want that. What else we got here? Okay, so here's just something random. It should make sense that in general, you're going to have some people overshoot and some people undershoot. So in the case of the 5-second thing here, so this is what we did on the notes the other day. So it should make sense that most people will be right about 5 seconds, but maybe not exact. And then the further you get on either side, on each tail from that value, you're going to have less and less data points that are there, which is why this idea of the sand is so helpful for my brain, because it says, well, how much sand is piled here at the top around the mean? Well, this is where the most sand is. This is the like ant's entrance to the anthill, right? So it's the stacked the highest. The most sand is right there. And then as you get closer to each tail, you have less and less sand as you approach these edges. You can't fit as many grains of sand down here. So this is why that anthill metaphor really works well for me. I hope it works well for you too. But estimate the percent of values within one standard deviation of the mean. That means every data point from here to here, how much percentage is that? What's the proportion of the data there? And if you just add 34 and 34, then you arrive at 68%. And like I said, that was 13.5, and then this one is 2.35, and then technically outside of the third standard deviation is 0.15. These are all percentages. It should make sense that once you add up each slice, you total 100%, and that is in fact the case. This is 13.5 in this slice, and then 2.35 in this slice, and 0.15% in the very tail. So as you see that, as you get closer and closer to the edges, there's less data there, and that makes sense because someone trying to stop the stopwatch on 5 seconds would probably not overshoot it by 5 seconds. So like they wouldn't stop the stopwatch at 10, I guess, unless they were messing around or they were just really god awful at estimating time. The whole point is that the further you go from the mean, the less data points there are, because the less likely you are to get a result like that. Somebody wouldn't start the timer and then immediately stop the timer, so they wouldn't get like 0.05. They wouldn't get like almost zero. So there's no not that there's no data. There's such little data out here that we just ignore it. We pretend it doesn't exist because it's so far away that there's no way that that's likely to happen. Because all the data, like I said, is stacked around the mean. So what's value is 2 standard deviations below the mean? That would be this data point, and 2 standard deviations above the mean, that would be this data point. So you just list those two, and then you can add up the chunks, the percentages, to figure out how much of the data is supposed to be within 2 standard deviations. If you add those up, you will arrive at 95%. The exact same thing happens for number 4 when you arrive at 99.7%. If you don't believe me, you can add it up. And then right here, use the normal distribution applet, which is this link, which I've already pulled up, and then you click on the normal distributions thing. So you go here, normal distributions, and this is calculate the area under the normal curve. So in this case, our mean was 5.02. Our standard deviation was 0.1. We plot it. So here is our normal distribution. This is the curve that we just made, like just now. And then we can calculate the area between two values, to the left of a value, to the right of a value, or outside of a region. So in this case, they want us to calculate the area between two values. And what are they asking us for? The actual percentage of values within one standard deviation of the mean. So the actual percentage of standard deviations will be from 4.92 up to 5.12. Now, in case there's any confusion on how I got these numbers, it wants to know within one standard deviation of the mean. So I took the value that is one standard deviation below, that's my left boundary, and one standard deviation above is my right boundary, and I plug those in. We hit calculate area, and we get a 68.27%. Like I said, this stuff up here, these are nice, easy numbers to just kind of commit to memory. They're not precise. They're close, but they're not exact. You'll end up finding that the calculator will give you the best answer. Stapplet will give you a really great answer as well. You could do the exact same thing for two standard deviations, which is 4.82. And then obviously, as you can see, as I change these, the graph will automatically update 5.22. Here's 95.45 instead of the 95%. So a little bit of a variation there. And then 4.72 up to 5.32. And there's 99.73. So this this rule, this empirical rule, or the 68, 95, 99.7 rule, as it's called, it's got more than one name, this always holds. This is always true. As long as you have a big enough sample size, this will always be the case for something that is normally distributed. If it's not normally distributed, you can't use the normal distribution. So hopefully that makes sense. It has to have this shape in order for this shape to apply. That's basically what I'm saying. And then for 6 through 8, we would be asking, well, in class, the stop sign is here so that I could tell you that I want you to answer these questions without using Stapplet. So this is a little bit tricky, but I can walk you through how to do these. So what percent of stopwatch times are less than 4.82 seconds? So what I like to do, I'm going to do some erasing up here. Where did I put pen? There it is. What I like to do, which you don't have to do, is I like to I'm going to erase all the things that are not important here. And then what I'm going to do is grab a very bright, vibrant color. So in this case, we'll use pink, but it doesn't really matter. And I'm going to color in the place that we're interested in. So what percentage of stopwatch times are less than 4.82 seconds? So I'm going to go to 4.82 seconds, and I'm going to color in the area that I care about, which is all the times that are less than that. And then, this is the question I always pose, how far do we go? Right? Well, in this case, this graph actually gets really thin all the way out to infinity, positive and negative infinity. So this technically goes on forever. So if this entire slice all the way out to negative infinity is 0.15, and then this slice is 2.35, all I have to do is add them together, right? So this is 0.35, sorry, 2.35 plus 0.15 will give you the total percentage of times that are less than this value. So 2.50. That's it. So the percentage of stopwatch times less than that is just the sum of those slices. Same thing for 7. What proportion of the stopwatch times are between 4.92 and 5.22? So we can do the same exact thing. We can do the same exact thing. We can go 4.92 to 5.22, and we're going to take this area. This is what we care about. These slices. It includes this piece, that slice, and it stops right here. So those are the parts that we care about. So all you do is just add up those chunks. So 34 plus 34 is 68. plus 13.5, 70, 80, 84. Is my brain working? Let me pull up a calculator just to be sure. All right, we want 34 plus 34 plus 13.5, and that's it. 81.5. All right, so Mr. Vallone's brain isn't working. So 81.5. 81.5, and that's percentage. 81.5%. Stopwatch time is at the 84th percentile of the distribution. The 84th percentile is where you have to stand along this x-axis. Let me erase the colored in parts. Is wherever you have to stand along the x-axis so that you have that percentage of data to your left. So you'd basically just be figuring out where's the area to the left going to be 84. Well, it should make sense to everyone that if I draw a line here, the area to the left is 50%, right? Because it's half and half. It's a perfectly symmetrical curve. So there's 50% of the data to the left, and I need 84. Well, 50 plus 34 is exactly 84. So there's now 84% of the data to the left of this line. So what place is this? What location? This is 5.12. So what stopwatch time? So now they're not asking for a percentage, they're asking for a time. 5.12. And then in this case, it's seconds. So 5.12 seconds is where you have to stand to have 84% of the data on your left. I'm not sure which direction is left in the camera, but I guess we'll figure that out. Okay, so there's the whole first page. This is basically how this rule works. Let's go to the answer key. And now you could take a moment and copy that down if you like. Feel free to pause the video at this point to take a photo, a screenshot, whatever. As you can see, the symbols down here look a little bit weird. These are the symbols. I believe we've already talked about these. These are the symbols for mean and standard deviation. So the symbol for mean is right here. It kind of looks like a U with a tail in the front. This is how I draw mine, so you'll see it drawn a little bit differently depending on who writes it. And then this is the symbol for standard deviation. This is sigma, and sigma is a Greek letter just like mu. So this is mu, this is sigma, and they just have their two meanings. They will have the same meaning for the rest of the course. So there's not like any trickery or fanciness going on. So our first two learning targets is just about the empirical rule and just, for the most part, memorizing these numbers and how to set up a chart like this. And then LT3 is assessing normality, talking about observing the shape, and this normal shape, this normalcy, applies to dot plots, it applies to histograms and stem plots. It applies to everything. You kind of have to have a specific set of data so that the empirical rule will apply, which means that it needs to be large enough. If it's not large enough, most of the time you'll find that you won't get quite exactly, say like on one standard deviation above and below, you won't quite get exactly 68% is usually what happens because there's simply not enough data there, or it's not normal enough. I think we see that in these examples down here. So in number one, make a histogram of the data. Boom, there it is. I would probably have used Staplet to just make it. The histogram, it looks roughly symmetric, single peaked, and somewhat bell-shaped. I would agree with that. It's not totally normal, but like, you know, overall the shape is there. It's not perfect, but that's usually what happens. And in this case, we have, I guess this is the data that goes along with the histogram. So we have a sample size of 36. So with a sample size of 36, that's not quite enough to guarantee that we're going to get exactly like the perfect normal distribution. which you find here in number 2. Use the summary statistics to calculate the percentage of data values within 1, 2, and 3 standard deviations of the mean. How closely do they match the empirical rule? So what you'd be doing is you just take the mean here. Here's your mean, here's your standard deviation. So here's your mean, here's your standard deviation, and you're going 1, 2, and 3 standard deviations above and below. That's what this plus or minus is. This is above and below at the same time. So it creates this interval. So this is 1 standard deviation above and below. This is 2 standard deviations above and below. And then this is 3 standard deviations above and below. And we know that this is supposed to be 68, 95, 99.7. However, because of our sample size of 36, we're not quite reaching those exact numbers. And this is kind of what I was saying earlier, is that if we don't have enough data, it's not going to be perfect. It's just an estimation. So then in number 3, they're talking to you about how, based on your answers, is the distribution usable for these refrigerators approximately normal? Explain your answer. And so these percentages are pretty close. So yeah. And then they slide in this special word here, approximately. Approximately normal. This is a way that in statistics we can get away with saying that something is something else, and still leaving us room to like be wrong. So approximately is a great word for that. Questions 4 and 5. Assume the population is usable side by side, approximately normal with a mean of 16 and a standard deviation of 1.2. Okay, so what this is saying is take out a separate sheet of paper or something and draw yourself one of these. That's a terrible one, but draw yourself one of these, put the mean in the middle, and then count up 3 and down 3. And now you can answer these questions here. So, about what proportion of side-by-side refrigerators have a usable capacity between blah, 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 and blah, blah, blah. Well, what you also could do, let's go back to the Statlet. New tab. You could also use Statlet for this, because what did they ask us for? A mean of 16, standard deviation of 1.2. So you just take it, mean of 16, standard deviation of 1.2, and then you click plot the distribution. Here's this. It's done for you. And now you can use these to answer whatever questions are thrown at you. So in this case, try to make this fit on the screen nicely. About what proportion of side-by-side fridges have a usable capacity between 13.6 and 19.6. And you hit calculate area, and it shows you the area. Now you may also notice that on the normal curve, at least on the Statlet, when you do these, it gives you this thing here, z equals. Technically, we don't know about this yet, but anytime you have a normal distribution, you can create this standardized score for it. We talked about standardized scores. I told you it's called a z-score, and then we stopped. But these standardized scores tell you exactly how many standard deviations you are above or below the mean. So at 13.6, if our mean is 16, you are precisely -2 standard deviations from the mean, which means you are down 2 standard deviations from the mean. So you're right here. And then if you were at 19.6, you are 1, 2, 3 standard deviations above the mean. So the z-score system is just a way to talk about position relative to the mean on the normal distribution. So it gives us this area. We list the area here. We're done. All right. Find and interpret the 16th percentile of the distribution. Okay, the 16th percentile. So there's a couple ways you can do this. You would be expected on a question like this, as of right now, because we don't know how to work backwards yet. You'd be expected to basically add up the chunks of the empirical rule, or the 68, 95, 99.7 rule, to get as close to 16 as you can. So that would mean that you're taking the lowest slice, the 0.15, and adding 2.35 and then adding 13.5, and that should total to 16%, or at least close enough to it. So then your it'd be this slice and this slice and this slice, so 14.8. Yeah, the 16th percentile of this distribution is 14.8 cubic feet. And if you like, you can check it. And I just changed this over to value to the left of a value, 14.8, and you can click calculate to see how close you are. So like I said, the empirical rule is an approximation. The calculator will give you the correct exact answer. So there's that. Okay, I feel like I, at this point, should start doing like YouTube intros and outros, but that's not really my vibe. So I'll see you in the next set of notes.